Okay. We are going to do 7 and 8 today. 7 is our range equation, and also looking at pulse repetition frequency, and how to get the pulse repetition frequency from other values. And then transducer, basic transducer design. I actually don't mind this chapter. It's the, I think towards the end of the semester, the equipment, chapter 15, 16 maybe. There's a lot of different transducers, and they have a lot of different names and a lot of overlap. It's very frustrating. But this chapter, chapter 8, is fun. So it's not fun, but it's tolerable. Okay, remember, so chapter 7. Ooh. I still, you know what, sorry guys. Okay, that should be better.
Hey, quick question. On chapter 6, do we have to know Snell's law?
I would be, you'll never be asked to work it out. So it's worth knowing. Just because I don't like it doesn't mean it won't be on the SPI. So anything in this book is fair game for the SPI. Although Bria was just telling me she went to the Edelman seminar. You guys can do that if you want. The Edelman made a lot of money just being this is the one thing he does is teach ultrasound physics, and he does a better job than me at really narrowing it down and teaching to the test. And so if you guys are interested in the seminar, I would go ahead and give it a try. We can get some information for you on that. And he would be able to say whether or not there's even a possibility of it showing up. As far as I'm concerned, if it's in the book, it's fair game on the SPI. Anyway, so range equation. Before I even write down the range equation, ultrasound machines are range finding equipment. They are same thing as a sonar, same thing as a fish finder, same thing. It's range. It's telling you how far away something is, and they're doing it by time of flight and speed of sound. And so we need to know what the speed of sound is. We assume, so let's see, the range equation is depth in millimeters. I always forget whether it's millimeters or centimeters. Millimeters per microsecond. That's soft tissue average. Remember that? It's not the only speed, it's just the speed that we have to make an assumption. And the computer has to make an assumption. And then they write in the book, go return time. And I guess that's worth writing go return, because it's two ways. We both create the sound, there's an echo, and then we listen to the sound. So it's two ways. Since it's two ways, we divide by 2. The range equation without going 2 ways is simply speed of sound times time. Not go return time, but just time. But we go both ways. So that's divided by 2. And then we mentioned the 13 microsecond rule. All that means is that when you input 13 microseconds into that go return time, it comes out to be 10 millimeters, which is the same as saying 1 centimeter. That's the rule. It's just that that's the number you plug in to get 1 centimeter of depth. And it's convenient because now we just, for every centimeter, we add another 13 microseconds. Or for every 13 microseconds, we add another centimeter. This is still review, so I'm going to keep moving. Well, then we get to something that's not so much. The pulse repetition period and maximum imaging depth. Now, this is page 109. When a sonographer adjusts the system's maximum imaging depth, the pulse repetition period is altered. We've kind of already talked about that. Recall that the pulse repetition period is the time from the start of one pulse to the start of the next. Therefore, the pulse repetition period of the go return time of a sound pulse, the 13 microsecond rule applies and the depth of view is shallow. When the depth of view is shallow, the PRP is short. Let me go ahead and draw that out again. So shallow imaging, let's say that's our maximum depth there. We have a wave there versus deep imaging. And we have our pulse there. Our return times. This is the echo going back. This is a relatively short pulse repetition period, whereas this one, we're waiting and we're waiting and we're waiting and we're waiting. So we have all of that wait time. We're imaging deeper. That is a long pulse repetition period. So now this could be, and I even wrote a little note that I feel like the wording is not perfect here. So let's look at this, page 109 still. I'm going to jump over the mathematical part and say, for example, when the depth of view is set to, no, I will write out the mathematical part. The pulse repetition period in microseconds is equal to imaging depth. I'll just say depth, but it's imaging depth. It's how deep you've set your machine to look. And let's see, centimeters times the 13-second microsecond rule. So microseconds per centimeter. So right off the bat, let's just do this. Cancel out our centimeters. So now we're just left with microseconds, which is what we're supposed to see, microseconds. So that was an easy to deal with those units. The pulse repetition period is equal to the depth times 13. So we've taken the 13 microsecond rule and kind of turned it around on its head. 13 microsecond rule says for every centimeter of depth, the go return time, or we'll just say time, but really it's two, remember it's always two ways. The time is 13 microseconds. 1 centimeter is 13 microseconds, 2 centimeters is 26 microseconds, and so on. We also know that the pulse repetition period changes with depth. This was a long PRP, that was a short PRP up there. So if we simply just take the, kind of like combine these two and maybe turn a little bit upside down on its head and say, Well, then that means that the 13 microseconds times the depth is how the computer figures out what the PRP, the pulse repetition period, should be. Let me state that again, because I actually find I have to, even though this seems rather simple, for some reason I have a bit of a time with this. The depth you set it at. Here's your screen. Here's 1, 2, 3, 4. Nice. Really, Kurt. Let's just make it really simple, actually. 1, 2. 1 centimeter, 2 centimeters. If I'm only imaging 2 centimeters and the 13-second rule says there's 13 microseconds of wait time for every centimeter we go, we know that for all the echoes coming back from depth, it's going to take, well, in this case, 26 microseconds for all those echoes to get back. So that tells the computer, well, you have to wait this long before you could send out your next pulse. So that affects your pulse repetition period. Now, the thing is, we don't say, like on your computer, you don't have pulse repetition period. You do have PRF. In fact, I was just looking at that on the screen with a couple of you today. We do have PRF on our screen. Well, we have it when Doppler's on. There's still a PRP and a PRF when Doppler is off. It's just, it's hidden from us because we don't have, we don't control it in the sense that we turn our PRF. We do control it through the depth button, right? Change our depth, we change our PRP, thereby changing our PRF. So PRF, remember, is the same as saying 1 over PRP. They're reciprocals of each other. So I have something written down, and it's best that I use what I have written down here. So, example for, let's do that. That's a nice color, blue, I think. For, let's see, so if we're imaging to 5 centimeters of depth, we can, let's get this, just so we can see that a little better. Actually, I can move that out of the way, can't I? Yes. This is just an example. So if we're going 5 centimeters deep and you want to find out what the pulse repetition period is, it's simply 5 PRP microseconds equals 5 centimeters. Whoops. Yeah. Times 13 microseconds per centimeter.
Yeah, that's why I said 65.
Oh, I didn't hear that before. Yeah, that's good. Exactly. Is equal to 65 microseconds. Now, did you take it one step further, smarty pants?
No, I didn't. You haven't taught us that.
1 over PRP So 1/65 microseconds. But if you're going to use your calculator, you're going to have to do 1 over, oh, do I have the right amount of zeros? 6, yep. 0.12345 So for its microseconds, the millionths is equal to 15,385 hertz, or let's see, maybe 15.4 kilohertz. And we'll see that, this is what we'll see on the screen. So that is the reciprocal. It doesn't seem like it would be, but that is the reciprocal of PRP. That's our PRF. So now we could simply find the reciprocal of PRP is PRF, and we have 15,385, and that's a pretty common number, I would say. So that's the amount of time. So remember, this is pulse repetition frequency. That's fifteen plus 1,000 pulses per seconds. And that's a pretty typical. Nowhere near the millions of our fundamental frequency, which each one of these little M&Ms, each one of these may have, let's just say 5 megahertz, but it's the equivalent of 5 megahertz, or it's like that waveform is 5 megahertz, but it's only being sent down as tiny little packets 15,000 times a second. Yeah. Oh, and then, and then there's another way of finding PRF. I honestly don't think it's, we have to, it's in the book, we have to go through it. I have a feeling it's one of those things that is probably not in Edelman's review. And Edelman's review is as I was told recently, Edelman's review is even smaller than the book here. It's less information in the book, because, and then there are other books that are 10 times as big as this, and you learn all that, and then they only ask you a few questions. So another way of finding pulse repetition frequency, if you do not have the PRP and you don't yeah, let me switch to the next page. Oh, this is horrible. Page 110. Speed of sound. In fact, let me just talk through most of this. Speed of sound in soft tissue is 1540 meters per second, which is the same as saying 154,000 centimeters per second. Sound can travel into tissue and return from a depth of 77,000 centimeters in a second. $77,000 centimeters in 1 second. So that seems a little crazy. 77,000 centimeters is bigger than most people. According to the book, it's almost a half a mile. But that also means that it can travel from a depth of 77 centimeters 1,000 times in a second. So in 1 second, sound can travel tissue depth of 77,000. 1,000 times, yeah, 1,000 times in 1 second. Or to a depth of 7.7 centimeters Now we're getting to normal imaging 10,000 times in a second. So normal imaging 10,000 times a second is perfectly probable. In essence, 77,000 may be a single round trip or divided into many thousands of round trips. So a single round trip, if you're gonna theoretically, you can go 77,000 centimeters or a half mile pulse and wait a full second to come back. That would produce a really slow image. When depth of view is shallow, the PRF is high. Mathematically in soft tissue, then, so I'm just gonna write the mathematical. Don't worry about this, guys. Don't worry about this one in particular. I mean, oops, 77,000 centimeters in a second. Don't worry about it in the sense that I don't want you to get bogged down with the math. The concepts are so much more important than the math. You do have to worry about it somewhat. Image depth in centimeters. So when the depth of view is set to 7.7, so just making super round numbers, we can go to a 77,000 centimeters per second divided by 7.7 centimeters. That is going to equal 10,000. So 7.7 goes into 77,000, 10,000 times. That is what your pulse repetition frequency is. So you know what, I'll do this one more because I actually have another example that brings us, it goes back to this number again, this previous number of 5 megahertz. So define the PRF, and we know we could do 77,000 centimeters per second, and we're given a depth of, let me move this over, damn it. Okay. Remember we used 5 centimeters over here to get to 65 microseconds. And we turn that over. We inversed it to find the PRF. So that's another way of finding the PRF. We found 15,385 hertz. So if we use PRF divided by 5 centimeters, we get an answer of 15,400, which is close enough. They don't always match perfectly. 15,400 hertz. So basically 2 ways of finding PRF. I guess both of them are good. 77,000 divided by the depth, or you find the pulse repetition period, which is 5 times the depth times the 13-second rule. And then to find PRF from there it's just a reciprocal, so you inverse it. Yeah. I hate math. So when I was a kid, I kind of had some learning
many years ago.
Yes, it is. It actually is many years ago. But when I was a kid, I had some serious learning issues, especially with math. And it affected me, it affected my psyche considerably. Now's the time, okay. Considerably. And to this day, like when I'm in front of a classroom and I start doing math, and I mean simple math, my brain just panics, I freak out and I can't do it. I go sit down at the desk and 2 seconds later, I'm like, oh, all right, I got the problem. So I get horrible anxiety. So if you guys ever see me just like forget what 2 + 2 is, it's because my brain is completely locked up.
That equals 7, right?
There's locked up and then there's defective. Okay, chapter 8, transducers. What is a transducer? I mean, so we know our transducer. By the way, when I'm with patients, I don't call it a transducer. I call it a camera, because that's what they understand. If you say transducer to a patient, they're like, I have no idea. We used to say camera. But I have to quickly be careful that I don't say camera when I'm talking to a radiologist or my fellow technologists, because then they'll think, do you not know what it's called? And no, I call it a camera to the patients, and then a transducer to everyone else. But what is a transducer? What does that? Right. So I know some of you are thinking it. So I will say a transducer is anything that changes one form of energy into another form. You can you could really stretch the definition of a transducer and say like a hydroelectric plant is taking the energy of that kinetic energy of moving water and making electricity. Your ear is taking mechanical energy for the bones, stapes, hammer. I'm sure Matt could tell me what the bones are, but in that those bones are moving with the sound and causing waves in the semicircular canal, which cause an electrical change in them, and that is what we interpret as sound. So your ear is a hammer. Yeah, thanks. Your eyes are transducers. The speaker, the speaker that I'm using right now, the microphone and the speakers are transducers. So anything that changes one form of energy to another form of energy. Let's see, transmission, piezoelectric effect, yes. So the piezoelectric effect, important to know. I'm sure it's written down here somewhere, but I'm just going to go by memory. Well, we know what electric means, right? Forming electrons. Piezo I believe means to push in Latin. So piezoelectric, so you push on or you hammer on a piezoelectric material, it forms electricity. It actually goes both ways. And so you could have, you could push and causes electricity, or electricity can come back and essentially push on the element. This may or may not be important.